curly H is the upper half plane. For simplicity, I will assume that H mod gamma has a unique cusp at infinity, and that the stabilizer of this cusp intersected with gamma is this subgroup. I will use the parameter S for the character delta to the power S over 2. Delta is the modular character of the Borel, so it boils down to this character. Just keeping with tradition, it's actually not the most convenient choice. A will be the connected component of the quotient B mod n, so A is the group, the multiplicative group of positive real numbers. And this identification is again by delta to the 1/2. And here are my basic spaces. Brackets H will be the automorphic quotient H mod gamma, and brackets H sub B is the boundary degeneration. In other words, it's the quotient of H by n times plus minus 1. N is all upper triangular matrices. So the action of the torus A on C infinity of the boundary degeneration will be normalized so that it is unitary. And then pi sub S will denote the S eigenspace. S means delta to the S over 2. So it is a principal series representation. M of S will be the standard intertwining operator. So it's defined by this formula. It goes from the principal series with parameter S to the principal series with parameter pi minus S. And finally, I fix measures. I fix a measure on H, H mod gamma infinity, brackets H, compatibly. All of these spaces are locally isomorphic. And then I fix a measure so that the fibers of this map have measure 1. Okay. And this is the new theorem that I want to prove. It's about half a century old, more than half a century old. So, as you know, L2 of H mod gamma decomposes into the discrete and the continuous automorphic spectrum. So now we take a function in the Schwarz space of H, a Schwarz function on H. We have fixed a measure on H, so we can convolve with this function. And is a rapidly decaying function together with its derivatives. So it decays faster than any polynomial. And the non-invariant Selberg trace formula includes this term and this term, which are extremely nice. The trace of the convolution operator on the discrete automorphic spectrum and the elliptic orbital integrals of our test function. But then it includes other terms. It includes this very mysterious term, which is, it's also an invariant term, but it comes from the continuous spectrum of this space. It includes an integral of logarithmic derivatives of intertwining operators over the continuous spectrum. And on the geometric side, it includes weighted orbital integrals plus the contribution of the unipotent orbits. So I never understood this formula.
What is the last term?
So maybe I shouldn't explain it. It's one way to write the contribution of the nilpotent, of the unipotent orbits. It's the constant coefficient of some zeta integral. It doesn't matter. So actually, I will not talk about the geometric formula at all because I have nothing to add to treatments that are already existent. I will mostly focus on the spectral side, and I would like to. My problem is that I never understood this formula, so I sat down to understand it, and I will try to answer the following questions: what is this formula computing? this is actually pretty well known. I will just review it and reformulate it. Secondly, why are these terms showing up? Is there a conceptual reason, for example, why the continuous spectrum should contribute discretely? So I don't know if there is a conceptual reason in the minds of, and what different people deem conceptual is a different thing. But I asked several experts and I didn't get a satisfactory answer. So I'll try to provide some answer to this question. Why is this term, for example, appearing? Another question that one can ask, I will not talk about it today, but what can we say about the invariant trace formula? What is this computing? Maybe I can say some things if I'm asked afterwards. Sure.
So the left-hand side is not a representation of G, yes? It's only a representation of the Heck algebra.
Here?
Yes.
No, it is a representation of G. So H is, there's no G, H. The group is H.
H is SL2R?
H is SL2R.
And brackets H?
Brackets H is H mod gamma.
Ah, without K. Just H mod.
Yes. Yes, I had curly H for upper half plane. I'll use it if I just need to draw something. Okay, let me actually write this. Is this visible? So I'm not going to write more on this board. I'll just write the definition. So H is H mod gamma. H sub B is the boundary degeneration H mod n times plus minus 1. And then there's the space H mod gamma infinity living over both of them. And notice that this arrow, by the way, is an isomorphism in the neighborhood of the cusp. And we're going to use this. Okay. Okay. Now, my motivation was not only that I wanted to understand this formula, I also would like to extend it. I'll mention this motivation because it's also related to the treatment I will present. I would like to extend it to the relative trace formula, which doesn't exist yet in full generality, and it goes as follows. The setting for the relative trace formula, let me say it now adelically, K a global field, A a string of adels, G a reductive group over K, so brackets G will be adelic mod rational points of G. And then we have two nice G spaces, typically two affine spherical G varieties, smooth, by the way. And we take Schwarz functions on both of them. And then for each of these spherical varieties, we form a theta series. Theta series means we just sum over the lattice of rational points, and that gives us an automorphic function. And then we have one automorphic function for each of those homogeneous spaces, and we take the inner product of these automorphic functions, and that's what the relative trace formula is as a distribution. And this distribution contains information about periods of automorphic forms and things that one would like to study. So this is the most general relative trace formula. Ideally, that's what it is, but of course, this doesn't converge usually.
So what is notation said? Or what is bracketing?
So bracketing will be inner product, but bilinear inner product. Is that what you're asking?
This is just the definition, yes?
This is my definition, okay? So my definition, whenever you see these brackets, it's going to be the bilinear inner product. You just multiply them and integrate them. It is the right-hand side.
The last quality is just a definition?
Yes.
But the relative trace formula...
Yeah, I'm saying this is what it is. This is what it is as a distribution, and the relative trace formula is going to be two different ways to write down this distribution.
So this is the geometric side, or
This is the definition of a distribution. This is a distribution on x1 cross x2. Okay, and this distribution. But the problem, no, the distribution doesn't make sense yet.
Because the integral
Ideally, this is the distribution, okay?
But anyhow, this should be like one of the sides of the, this is like the
No,
side?
no, no, no. This is a definition of a distribution. This is...
And this is nicer. This is also...
This is not one of the two sides.
This is an idea, and then two sides are...
So the trace formula is actually a special case of this when you take the two varieties to be the group H, and when you take G to be H cross H, then the theta series that I wrote upstairs is just the kernel function, defined this way. And then what we are computing is the inner product of two kernel functions. But what is the inner product of two kernel functions? These are kernels for some operators. So their inner product is the Hilbert-Schmidt inner product of these operators, which is the same as the trace of the operator corresponding to the convolution of the two functions. So we will actually take this point of view instead of trying to compute a trace. By the way, none of these sides exists if H is not compact, if brackets H is not compact. But we will take this point of view instead of trying to compute a trace, we're going to try to compute the inner product of two kernel functions. Now, the basic issue in all cases is that one ends up having to compute inner products, non-convergent integrals of what I will describe in a moment is asymptotically finite functions on brackets G. This is a notion that I will describe in special cases afterwards. In general, I describe it here. So whenever you want to integrate theta series, whether it is for the theta correspondence or whether it is for the relative trace formula, you always end up having to integrate what I call asymptotically finite functions. And I will explain in the next slide in simple examples what this means. So what is asymptotically finite functions? Kasselman has described them in the case of rank 1. He calls them extended Schwarz space. So let me explain on upper half plane mod gamma. A function is asymptotically finite with exponent s if up to a rapidly decaying function, up to a Schwarz function, close to the cusp, it is equal to a multiple of y to the 1 plus s over 2. Y to the 1 plus s over 2 is this normalized exponent delta to the s over 2 that I had before. So the space of asymptotically finite functions with exponent s fits into this short exact sequence. It contains all Schwarz functions, and as a quotient, it has this principal series representation that I defined. So you end up having to integrate functions like that, and these integrals may not converge, but something that I learned from Joseph is that these integrals do make sense usually. So if you want to define an invariant pairing between those two spaces, even if at the neighborhood of the cusp these functions grow very fast, you can integrate them. The only case you cannot integrate them is when the sum of the exponents is equal to 0. And here's how the integral works. You take the product of the two functions that you want to integrate, and you multiply them by this delta. So let's keep in mind what is this capital delta. This capital delta is this little delta to the 1/2, basically, right? So you take an Iwasawa decomposition, bk, and this capital delta function is some height function. So this capital delta function is this little character delta 1/2 of b, and you multiply by this in the neighborhood of a cusp. U denotes here a neighborhood of the cusp. So when the real part of t is very small, this becomes a convergent integral, and then you meromorphically continue. You're going to get a pole at S1 plus S2, but then if S1 plus S2 is not equal to 0, you can take the analytic continuation to t equals 0, and that gives you an invariant inner product. It gives you an extension of the inner product on the Schwarz space. Okay? So this can be repeated in higher rank. So let's discuss now what happens with kernel functions. So the first realization is that when we try to regularize the Selberg trace formula and make sense of these non-convergent things, it's a rank 2 problem. Although we're dealing with SL2, from this point of view, it's a rank 2 problem. So G here will be H cross H. This is where our kernel functions live. And now I'll try to describe to you what is the asymptotic behavior of kernel functions and why these integrals diverge. So let me start first with a compactification of H, the reductive Borel-Serre compactification. This is when you add a P1 of R, when you glue a P1 of R to brackets H. And let me be a little bit pedantic about how you do that. Of course, one can draw a simple picture of the fundamental domain, and then at infinity you put a, well, actually here you are modding out by k, so here you will just put a point at infinity, but that's because you mod out by k. If you don't mod out by k, you will put a P1 of R. Let me be a little bit pedantic about how this works. So this H sub B, which is just H mod n, it has an action of the torus R star. This space has an action of the torus R star plus. And now I compactify R star plus by adding a point at infinity. And then I take the product of this compactification with my space and I divide by the diagonal action of R star plus. So that adds up another orbit to that space. I pull it back here and I glue it here. Now, let's do that now for H cross H. Of course, we could be working with the reductive Borel-Serre compactification of this space, which would be just the product of the two. In terms of toric varieties, so here we have, if you think of G sub B, which is just the boundary degeneration of H twice, so here we have an action of twice the torus. So the reductive Borel-Serre compactification of that would correspond to the toric variety that you get by adding a divisor, if this is the Lie algebra of the torus, right? So you would be adding a divisor in this direction, A plus, and in this direction, A plus. So this is the Lie algebra of A squared. So you would be adding a divisor here and a divisor here. That's not what we want to do. We want to blow up the intersection of these divisors and just keep this blow up. So we want to compactify in the diagonal direction. Add a divisor here. So I do this compactification for the torus R star squared. I do this compactification for the torus R star squared, and then I repeat the same process. I glue this to the boundary degeneration. I pull this back here. I glue it here. Okay? So that gives me a diagonal compactification, so to speak. It's a partial compactification of my space, where, except for the original orbit, I also have an orbit which is now isomorphic to what have I glued to that space. I have glued this thing. I have glued the boundary degeneration of G, which is 2 copies of that space, modulo the diagonal action of the torus. And now I let capital pi S be all Schwarz sections of this character. So what does this mean here? It means all eigenfunctions, it means eigenfunctions on this space of the diagonal torus with this character under the normalized action. And then I take Schwarz sections. Now, notice that the notion of Schwarz sections makes sense, although these are not functions, they are eigenfunctions. The reason is that the characters are of polynomial growth, and Schwarz means decaying faster than polynomial. So the picture here is the following. As you approach, so so I'm talking about I'm describing a sheaf over sections of a sheaf over this orbit at infinity, and I'm saying that along the diagonal torus, along a diagonal, my sections vary by a certain character. But in transverse directions, they are of rapid decay. And this makes sense no matter how I take my transverse direction. Of course, I have to take it in a polynomial way, because rapid decay means decaying faster than polynomial and the characters of polynomial growth. So this makes sense. So I take Schwarz sections here, and then I say that a function is of a function is asymptotically finite so then I will say, here's the proposition, the kernel function belongs to the space of asymptotically finite functions with respect to a certain character, with respect to this compactification. Let's look at this short exact sequence to explain what I mean. We have rapidly decaying functions on G mod gamma. They live in a space of functions which, close to this divisor that we have added at infinity, behave as eigenfunctions for a diagonal with respect to the given character. This is a description of kernel functions. So they are not rapidly decaying, of course, otherwise all integrals would make sense. They are functions on brackets G which extend to sections of this sheaf over the compactification. Close to the extra orbit that I have added, they behave like eigenfunctions for a diagonal. So this is a generalization of the example of the one-dimensional example that I gave before. Unfortunately, the character by which they vary, this delta to the s over 2, is with s equals 0. And that means that if I try to define the regularized integral of two kernel functions, even in the regularized sense, it doesn't exist. There is no invariant distribution, invariant way to extend the inner product to those functions. So what the trace formula does is the following. It takes one of these kernel functions and modifies it to a holomorphic section where we change the character. If we change the character from 0 to arbitrary s, then the regularized inner product makes sense. And then if we vary this s, we're going to see a simple pole at s equals 0, a constant coefficient, and then something that goes to 0 when s goes to 0. So here's one way to define the Selberg trace formula. I take my kernel function, one kernel function, and then I take this modification of the other kernel function by s. I consider this Laurent series, and then I take the constant coefficient of the Laurent series. I could take the -1 coefficient, but that only includes information about Eisenstein series. So it's the 0th coefficient that contains the information about but unfortunately it's not invariant. So this is the Selberg trace formula, except that I have many ways to deform my section. So what I will do is I will deform it in a very specific way. That's what people in the trace formula do. I'll take my kernel, remember my little phi is the kernel function, the second kernel function. I'll take my second kernel function and I will multiply it by this height function to the s in the neighborhood of the cusp in the second variable. Are there any questions at this point? Should I explain again this asymptotics maybe? Okay. So, so the definition of the trace formula, one possible definition is this, that the trace formula is this, you take this deformed inner product of the kernel functions, and then you take the constant coefficient of the Laurent expansion at s equals 0. This is equivalent to the definition of truncation. Namely, you can take the convolution of the two functions and then integrate it over the diagonal removing a neighborhood of the cusp that's the neighborhood where this delta function is bigger than e to the t. Then you will see the same coefficient showing up, and it's the constant coefficient that one chooses to call the Selberg trace formula. So now my goal is to discuss the spectral decomposition of this and see where all these mysterious terms come from. I will not discuss the geometric side because by this equivalence you can see that I have nothing to add to the geometric side. So this equivalence immediately reduces you to the weighted orbital integrals. But the general question now that we have analyzed how it fails to be convergent is, what does it mean to spectrally decompose the inner product of two asymptotically finite functions? What is the meaning of Plancherel decomposition for asymptotically finite functions? Can we make sense of this notion, although those functions do not live in L2? And the model for that is actually the torus. So let's try to play this game with a one-dimensional torus. First of all, let's start with Schwarz functions on the torus, rapidly decaying both at 0 and at infinity. We consider their Mellin transform that gives an isomorphism between the Schwarz space and the Paley-Wiener space of holomorphic functions which are of rapid decay on vertical strips. Entire functions which are of rapid decay on vertical strips. Mellin inversion gives you the inverse map. And it can be taken as an integral on any vertical line. Now we're going to extend this to asymptotically finite functions. Let's start with functions which are asymptotically finite in a neighborhood of 0. That means our functions will be a multiple of x times, or a multiple of x to the s up to something of rapid decay, close to 0. And close to infinity, they're still of rapid decay. So what happens to their Mellin transform? Their Mellin transform now will have a pole, that's what is indicated here with S. Their Mellin transform will have a simple pole at S. But this is still an isomorphism, and the same Mellin inversion formula holds as long as you take sigma to be very, very small. Similarly, you can take functions which are asymptotically finite at infinity with exponent s. And then same story holds, except that for the Mellin inversion, you have to take sigma very, very large. So we can develop here a nice dictionary to play with these kind of functions. These are elementary problems. What will happen when we have exponents both at 0 and infinity? Well, now the poles at S will mix. We have to separate them. So the way to separate them is to include as part of our data of our Paley-Wiener space, not just the meromorphic function, but also charges on its Laurent expansion. Namely, we will split its the polar part of the Laurent expansion into positive and negative, and then we will account for it when we come to Mellin inversion. An example is, take the constant function. The Mellin transform of the constant function is 0. However, it has non-trivial poles, plus and minus, and you can put them into Mellin inversion. You see the Mellin inversion here only takes the plus part of the residue when real part of S is less than sigma, and the minus part of the residue when real part of S is greater than sigma.
So your two terms with denominator z minus s, this is what usually written like z minus s plus I0 and z minus s minus I0.
Okay, so there's already this formalism. I don't know. Maybe you can let me know about this. Yes, perfect. Okay, so we have this Mellin inversion formula. And we can also apply it now to convolutions in order to obtain a notion of Plancherel decomposition for these asymptotically finite functions, we're going to, the Plancherel decomposition will be expressed as a continuous integral, and then discrete contributions, which, let me go to the last line here. Suppose I bring the line of integration to the unitary line, sigma equals 0. Then what are the discrete contributions? The discrete contributions will come from superunitary characters, characters which are bigger than 1 in absolute value, that appear either at 0 or at infinity in every direction. And something that I didn't remark before, it's here in this remark, is if this line of integration happens to fall, and this plays a role in the trace formula, if this line of integration happens to fall on a pole, then you have to take principal value integral and 1/2 times the residue that appears. Okay, so this is very elementary, nothing to do with automorphic forms, but it will turn out to explain everything that we see in the trace formula. Any questions? Okay. So actually, we can a little bit allow ourselves to relax this notion of asymptotically finite. We can ask that one of our functions, let's say f2, is asymptotically finite up to a smooth L2 function. That means that it has some big exponents, and then if we remove them, then it's a smooth L2 function. Then it's Mellin transform. So let me show the picture here. Let me draw a picture. So it could be that one of our functions is, let's see, rapid decay at 0. Okay, so one of our functions would be of rapid decay at 0, and then it can have exponents. The other can have exponents here. Here it can have exponents and then some garbage. This garbage that we don't want to deal with will eventually have to do with poles of Eisenstein series, the bad poles of Eisenstein series that Bill Castleman told us we shouldn't be messing with. So in that case, the Mellin transform will only be defined in some half plane, and maybe also on the unitary line, and sometimes we can relate the two. So here's an example where it will show up. It will show up in the Radon transform on a function on H mod n. So if we take the Radon transform of a function on H mod n, then well, I'm a little bit worried now that I tried to simplify too much by doing SL2R. I was thinking of the Adels. But
What is your problem?
I don't mean the local Radon transform at the real place. I mean the global Radon transform over the Adels. Yes, I mean the global. Yes, I tried to simplify too much. So how to fix that very quickly?
You can't fix your slides, that's the trouble with it.
Yeah, that's a problem with slides. So,
Move to the next page and write on the board.
Slide to the next page.
yeah, so really here, I'm sorry, I kind of, preparing the slides, I kind of oversimplified. So I'm thinking here of having a function on H Adels mod n Adels, and maybe AK, and then F, and then Radon transform of F will also be a smooth function on the same space. It's given by this formula that I have written here. But when we decompose it spectrally, in terms of its Mellin transform, you see the global intertwining operators appearing. Yes, I think I mixed. I shouldn't have written my slides. I should have written them adelically, but anyway, so I apologize for that. So here you see that the Radon transform includes all the poles of the intertwining operators, but at least all the way to the unitary line we can control them. There are finitely many, for example. And then beyond that, there is some mess that we don't want to deal with. So this is what is going to show up in the slides that are coming up. But let me move to the spectral decomposition of the trace formula. So recall what we want to analyze is the inner product of kernel functions where we have modified one of the kernel functions to make it S asymptotic instead of 0 asymptotic. So let's take capital phi to be the first test function. Little phi s will be the kernel function for the other one modified. And I will use a dagger for the asymptotics of this kernel function. So the asymptotics of this kernel function lives in these Schwarz sections of a sheaf over GB mod A diagonal. And we can define a similar space of asymptotically finite functions for the boundary degeneration with exactly the same short exact sequence. And now we're going to imitate the Selberg-Langlands argument for the spectral decomposition. Namely, we are going to take a test function on the boundary degeneration, except that our test function now will not be compactly supported or Schwarz, but it will have exactly the same asymptotics as our kernel function. So we will take f to be a test function on the boundary degeneration which has, towards this divisor at infinity, has this multiplicative behavior. And then we will modify it to get a multiplicative behavior parameterized by the character s. And then we will form the pseudo-Eisenstein series of that. And a very easy lemma is that the pseudo-Eisenstein series ends up in the desired space of functions, asymptotically finite functions on brackets G. And it has the same asymptotics as the function that we started with. So I remind you that in the classical Langlands theory, Selberg and Langlands spectral decomposition, you start with a Schwarz function here, and the pseudo-Eisenstein series gives you a Schwarz function here. So now our functions will not be Schwarz anymore. They will have these prescribed asymptotics, but the asymptotics are preserved by the pseudo-Eisenstein functor morphism. It's very easy to show. So capital delta is this function that I'm using always to modify my behavior at infinity. So I have an Iwasawa decomposition H is bk, and then capital delta of b times k is delta 1/2 b. So if I have a function f which is in this extended Schwarz space with parameter 0, then the function f of h1, h2, delta to the s h2 will be in this Schwarz space with parameter s. Delta small is the modular character. So delta small is delta 1/2 of A inverse is absolute value of A. So, okay. So moreover, we have seen that our kernel functions live in a space like this, and if they lived in a Schwarz space, we know from a result of Kasselmann that the Schwarz space decomposes into its Caspidal and its Eisenstein part. So cuspidal here, I mean that because I have G is 2 copies of H, by cuspidal I mean cuspidal at least in one of the 2 copies. So, and this result easily extends to this extended Schwarz space. It decomposes into the cuspidal part and its Eisenstein part, and moreover the pseudo-Eisenstein series, the image of pseudo-Eisenstein series is dense in that part. All of these are Frechet spaces, by the way. So, moreover, the cuspidal part is the usual cuspidal part. You don't get anything by this, anything more in this extended Schwarz space. So that means that the cuspidal decomposition of this inner product is completely trivial. We can skip it and immediately assume, focus on the part of the kernel function that's inside of this part. And in doing so, we're going to replace, we are going to replace our modified kernel function by a pseudo-Eisenstein series. And start the spectral analysis of Selberg and Langlands. So the inner product of a kernel function with a pseudo-Eisenstein series by adjunction is equal to the constant term times our test function. And now the lemma is, that's the lemma that allowed me to state the proposition about the asymptotics of kernel functions. It's a very easy lemma. It relies on Brouhat decomposition. It says that the constant term of kernel function has 2 summands. These 2 summands correspond to the Brouhat decomposition. One summand is the kernel of the action of my function on L2 of the boundary degeneration. And it's given by this very simple formula, just integral over the unipotent in the middle. That's one of them. And the other is an integral over 2 copies of the unipotent. So you can write it as a Radon transform of the former, either in the first variable or in the second variable. So let me explain now where these 2 functions live. These 2 functions, one of them is essentially invariant under the diagonal action of A and of rapid decay modulo that. It's actually not invariant because I'm considering the normalized action, but it lives in this space. So here's the picture, and this is the basic picture to remember. We're discussing the now I'm going to draw a picture that's supposed to represent GB. Here's the cusp. So we're discussing the asymptotic behavior, we're discussing the constant term of the kernel function. And I'm saying that the constant term of the kernel function has 2 components. One component is essentially invariant under the diagonal, but of rapid decay modulo that, essentially compactly supported modulo the diagonal. The other component is the Radon transform of that, which is invariant under the anti-diagonal. And since it's Radon transform of something, it's what was included in the previous slide, it's going to be of rapid decay close to the cusp, but it's going to be a little bit harder to control in the other direction because it includes all these poles of Eisenstein series of intertwining operators. So we have to compute the inner product of our test function with these 2 summands. And we're going to do it one by one. So the inner product with the anti-diagonal term, I'm starting from this one because this is compactly supported. This is actually convergence. I don't know if is the red here clear? So the red is the support of the red is the support of our Radon transform. Okay? Our test function is what? Our test function is blue color here. Our test function is an asymptotically finite function in a neighborhood of the cusp. Remember that we have blown up and put a divisor here. So our test function is supported close to the cusp. the other is supported away from the cusp, the inner product is convergent. And this inner product will explain the mysterious term that showed up in the trace formula, namely, since one of the functions is invariant under the anti-diagonal action of the torus A, we can also make the other one invariant under the anti-diagonal of the torus A, and then we end up with a one-dimensional toric picture that looks like this. So we end up with inner product of two functions on the torus, essentially, where one of the functions is this asymptotically, is coming from this asymptotically finite function, so it is going to be of rapid decay away from the cusp, and it's going to have some character towards the cusp, and the other function will be rapid decay close to the cusp and have some characters corresponding to poles of Eisenstein series in the other direction. And then from what we said about Mellin transforms of asymptotically finite functions on the torus, we deduce that we have a continuous term which is a principal value integral over the unitary line of Mellin transforms. And then discrete terms which correspond to the asymptotics of these functions. And the asymptotics of these functions are the following. Well, we have the poles of intertwining operators that will give you the asymptotics that correspond to the asymptotics of this guy, to the exponents of this guy. Those are the poles of the negatives of poles of Eisenstein series with real part of S greater than 0. And then a discrete term that falls right on the unitary spectrum. That's why it comes with a coefficient 1/2. And this coefficient 1/2 becomes 1/4 when you compare the residue that you take in the diagonal direction with this. What is this? Let me explain what this is. So this will have to do with the exponent of our test function. So it will depend on the asymptotics of our test function, but the asymptotics of our test function live in the space. So our test function is this f sub 0. Its asymptotics is the f sub 0 dagger, and this lives in the space pi naught that I wrote before. Pi naught was Schwarz space of A mod, what is it? GB, diagonal. But I have already modded out by the anti-diagonal, so this will actually contribute only at those characters which are both invariant under the diagonal and the anti-diagonal. And those are quadratic characters. Those are the discrete contributions of the continuous spectrum to the trace formula. Does that make some sense? I know that it's a little bit...
Say it again, what you just said about quadratic characters.
Yeah, so adelically, this is the sum of all quadratic characters, right? So what are quadratic characters? I mean, induction, parabolic induction from quadratic characters. What are quadratic characters? These are the only characters that are invariant under both the diagonal and the anti-diagonal copy of the torus.
But more specifically, the only principal series which reduce.
The only principal series?
Which reduce.
Maybe, but that has nothing to do with...
I think it's actually...
Anyway. So from this point of view, the reason why this term shows up is that you end up having to integrate a function which in this direction is has a certain eigencharacter asymptotically, and with a function which in this direction has a certain eigencharacter asymptotically. Simple Mellin analysis on a two-dimensional torus will convince you that you need a discrete contribution coming from the characters that are invariant under both this and this direction, this subtorus.
What was the character?
This is the trivial character. We're inducing from trivial character.
Quadratic characters, one quadratic character is zero.
Yes.
Somehow it should contribute something different.
What do you mean different? These are not characters of the group. These are characters of the levy.
Yes.
Right?
So this particular trivial character is also quadratic character.
Yes.
Does it contribute?
So actually, I don't see quadratic characters at all here because I'm only decomposing with respect to this r plus star. So these are all trivial characters for r plus star. I don't see any. Okay. And then we also have the inner product with the diagonal term. The inner product with the diagonal term is the one that doesn't converge. So in this picture, the diagonal term is this black. So the diagonal term is the kernel of the operator acting on the boundary degeneration. And then we have to take its inner product with our asymptotically finite function. Both are in the same direction. And when we take S to be equal to 0, that's exactly when the regularized inner product does not make sense anymore. So we do need to deform our S. But when we deform our S, then the regularized inner product makes sense. Since one of them is essentially invariant under a diagonal, we can also make the other one this way. And then modulo the diagonal, both are of rapid decay. So the only thing that you see is a continuous integral of the corresponding Mellin transforms. And then when you start analyzing this integral, you use the intertwining relation that says that the Mellin transform of this guy, what is the Mellin transform of the kernel function? The Mellin transform of the kernel function lives in this representation pi sub z tensor pi sub minus z. The Mellin transform of the kernel function is simply, or if you want, you can think of it as living in the endomorphisms of pi sub z. The Mellin transform of the kernel function is really the image of phi in the endomorphisms of pi sub z. That's what it is. And because pi sub z and pi sub minus z are isomorphic, the intertwining relation gives us this. And moreover, the way we have chosen our section, we can write the Mellin transform of f sub s in terms of Mellin transforms of f. I know these slides are going to be a little bit hard to follow, and it doesn't really matter. What matters is what is the process that one follows. So you use this symmetry in order to write this as an integral from 0 to I infinity of the kernel function against the Mellin transform of f together with these intertwining operators. M1 and M2 refer to intertwining operators in the first or in the second argument. I want to emphasize that at this point that this is an absolutely convergent integral. And it will stay absolutely convergent if I take leading coefficient at constant coefficient at S. The reason is that here I'm applying intertwining operators on the unitary line. I know that they are unitary. And when I take coefficient, like constant coefficient at S, I'm taking constant coefficient of this guy at S. And this I control very well because this guy is Schwarz up to this asymptotically finite behavior. So this is an absolutely convergent expression. Now I can modify it in such a way that here instead of z, I have z plus s because that's what I need for that. I'm actually, at this point, I'm cheating a little bit. This minus s became plus s because I'm only interested in the constant coefficient. I didn't want to enter all these details. So this minus s and plus s when you're interested in the constant coefficient of the Laurent expansion at S, it doesn't matter, obviously, if you change plus S to minus S. So I'm cheating a little bit here. But you can modify this expression, write it as a sum. The integral of the sum is a priori absolutely convergent. And now if you put everything together, everything that we have seen, you get a big continuous integral.
Where did the derivatives come from?
So now I'm taking the constant coefficient of the Laurent expansion. Okay? So the derivatives come from the fact that a priori you are given coefficients at z, and you want to modify them to make them at z plus s, so you add and subtract the z plus s. So you end up having a difference between intertwining operator at z plus s and intertwining operator at z. Okay? And the reason is that these guys came from the other side. They came from the symmetries of this guy. So taking now the constant coefficient of the Laurent expansion, you do see the derivative, and you do see the constant coefficient of the Laurent expansion here, of this guy. This guy has a pole at S equals 0 because my F is asymptotically finite with respect to the given character. And this big continuous sum, the first, everything that's in the square brackets here can be interpreted as the Mellin transform of the constant term of little phi. Little phi was the pseudo-Eisenstein series of F. So when I take pseudo-Eisenstein series and I compute its constant coefficient, I end up with these 4 terms corresponding to the 4 elements of the Weil group. So these 4 terms here can be compactified to this term. So to sum up, the main theorem is that if I want to compute the inner product of a kernel, so if I have a kernel function, inner product with the deformation of an asymptotically finite function on brackets G, then I have a formula, and this formula includes the automorphic discrete spectrum, this discrete term coming from the continuous spectrum, which came from, again, it came from this, the inner product of this with the anti-diagonal term, and a continuous integral which is a priori convergent, and it comes from, it includes the inner product of this kernel function with the constant coefficient of phi check. Sorry, here it should be, like before, it should be the phi b check. It should be the constant term of phi. And then this term that includes derivatives of intertwining operators. So the proof is that we've already proven it for pseudo-Eisenstein series, and the whole space of asymptotically finite function is the sum of pseudo-Eisenstein series and Schwarz functions. So for Schwarz functions, if your pseudo-Eisenstein series was already Schwarz, you would end up with an expression that would not include these terms. And the expression is, both sides of the expression are obviously continuous. So they can be extended from pseudo-Eisenstein series to the whole Schwarz space. So you end up with this expression that holds for all asymptotically finite functions. And then if you want to apply it to the trace formula, you will see that this term will vanish. Why will this term vanish? This term will vanish because, for the same reason that we said in the torus case, when you consider the Mellin transform of the constant function, it's 0, except that it has a pole at 0. It's this funny thing that the function is 0, but it has a non-trivial Laurent expansion at 0. So saying with our kernel function, its Mellin transform away from, for s not equal to 0 is 0, although it has a pole at s equals 0. So this coefficient will vanish for our kernel function, and you are left with this expression, which is the spectral side of the trace formula. I hope I gave some, obviously this is not very easy to follow this kind of calculations. I hope I gave some rough idea for what the argument is. And thank you, Joseph, and many happy returns. This photo is from when Joseph arrived to Greece. I was very proud that I brought him on my little Greek island.
Any questions?
Yes, and since the mechanisms of how to actually push it.
Yes, my goal is to push it to arbitrary relative trace formula. So like I said, I have shown that on the geometric side, you always end up with asymptotically finite functions. And on the spectral side, again, by analyzing constant terms, you will see again that you get asymptotically finite functions that are determined basically by the structure of Borel orbits on the spherical variety. And the goal is to extend the Plancherel decomposition of Langlands to this bigger space of asymptotically finite functions. I see some difficulties which basically have to do with shifting contours. These difficulties do not exist in the function field case. Already for the function field case, it should be doable. In the number field case, there are a lot of things that I personally don't know and maybe are not known about Eisenstein series. They're related to the issues that Kasselman was discussing this morning. There may be fundamental difficulties in shifting contours, but hopefully with the things we've been discussing before, they might be resolved.
Any more questions?